Hello everyone, I am Burak ŞENCAN, responsible for power electronics hardware design. Alperen ŞENAY worked on PCB design and microcontroller programming, and Yusuf ŞİŞMAN handled power calculations and schematics, while Ömer BENLİ focused on simulations and supported the power stage. Our project addresses a common issue: charging devices on the go. Smartphones, tablets, and wireless earphones are essential in daily life, but keeping them powered, especially away from outlets, is still a challenge. Power banks add portability but still need cables. Wireless chargers remove cables but aren't portable. We aim to combine both solutions into a compact wireless power bank. Our design features a 5000 mAh lithium-ion battery, delivering up to 15 watts wirelessly under the Christ standard. It runs at a switching frequency of around 150 kilohertz, supports 1 to 6.5 amps, and maintains at least 70% efficiency. We designed within strict size and weight limits while adding magnetic alignments. The system works by converting 3.7 DC from the battery into high-frequency AC using a full-bridge inverter. This AC is stepped up by a 1 to 5 transformer, then delivered to a transmitting coil which sends power wirelessly to the device. Every stage from battery to coil was carefully designed and simulated for compactness and efficiency.
In this part of presentation, I will explain the implementation phase of our project. Our wireless charger is composed of three main blocks: a power stage, a control unit, and voltage regulation modules. These parts were designed and integrated with the goal of efficient and safe wireless energy transfer. Starting with the power stage, we used a full bridge inverter composed of four MOSFET driven by a gate driver. The inverter operates at a frequency of 150 kHz. This generates high-frequency AC, which is suitable for wireless transmission. Uh, to match the voltage levels and provide isolation, we designed a custom toroidal transformer using a ferrite core and lead wire. The 1 to 5 turns ratio allows voltage step-up and enhance magnetic efficiency while minimizing electromagnetic interference. On the regulation side, we implemented a boost converter to step up the voltage to feed gate driver. A buck converter is used for feeding a microcontroller. These modules were tested and validated using an oscilloscope. For the control unit, we used Arduino Nano microcontroller to generate precise PWM signals with built-in dead time. It was responsible for synchronizing the switching of the MOSFETs and ensuring stable operation of inverter. The code was carefully developed to maintain timing accuracy and avoid shoot-through events. In addition to PWM control, the microcontroller was also used to monitor system performance and provide adaptability in the future design improvements. Uh, can we go on? Finally, we assembled the PCB manually and verified the complete system. The result was a fully working prototype capable of charging a smartphone wirelessly, with all the function blocks performing as expected.
Hello, I am Yusuf ŞİŞMAN. Today I will be presenting the testing stage of our project in detail. To begin with, I would like to start with the buck converter unit. As you can see in the photos, this unit is responsible for stepping down the voltage. It reduced the input voltage from 3.7, which is supplied by the lithium-ion battery, down to a stable 3.3 volts. This level is required for powering certain low voltage component in our circuit. Next, we process with testing the boost converter. In this stage, the circuit performs the opposite function, stepping up the 3.7 battery voltage to 12 volt. The testing involved checking the output stability and confirming the converter's efficiency. Another important part of our system is the PWM signals, which are visible in the oscilloscope captures shown. These signals have a frequency of 115 kHz and are used to drive the gate driver of the converter. We adjusted the duty cycle and monitored the waveform shapes to make sure the switching was efficient. One of the key elements in our design is the transformer. It was custom hand-wound by our team to meet the specific requirements of our circuit. The transformer has a turns ratio that provides a voltage step-up factor of 5, which plays a critical role in the energy transfer within the isolated converter stage. Finally, we carried out the overall system integration test. This involved assembling all components on a single board and observing their interaction under real-world operating conditions. The final version of the complete circuit, fully soldered and assembled by our team. That concludes the overview of our testing process.
Hello, I'm Ömer BENLİ. In this part of the presentation, I will talk about the cost analysis, commercial use, certification, and safety features of our wireless power bank. First, our prototype cost was about 2,600 Turkish liras. This is a bit high because we used imported parts and made only one device. But if we produce more units, the cost will go down. We can also save money by using local suppliers and by offering optional features. Next, we think our product is good for students, travelers, and the people who use their phones a lot. It's portable, wireless, and has a modern design. To market the product, we can make videos for social media, work with influencers, and show it at universities. About standards, we followed rules like IEC for safety and the QI standard for the wireless charging. Also, we checked local Turkish standards. For safety, we used a special transformer to protect the user from the high voltage. We also added insulation and a small delay time to avoid short circuits. Finally, our design is good for environment. It uses safe materials and produces less waste. It also helps people with disabilities because they don't need to plug in a cable. Thanks for the listening.